So picking up with Advanced Engineering Mathematics Practice Final Exam, Part 3, number 7 here. Find the full SVD of A equals first row 3, 0, second row 4, 0, third row 0, 5. Then determine the best rank 1 approximation. So this is a singular value decomposition problem. So our A is what's given there, 3, 0, 4, 0, 0, 5 respectively for those rows. So computing A transpose A, that equals 25, 0, 0, 25 for the first and second rows respectively. So both singular values are sigma sub 1 equals 5 and sigma squared equals 5. So we're going to choose here V sub 1, that's this column 1, 0. V sub 2 is this column 0, 1. So from there, U sub 1 equals A, V sub 1 over 5. And that's going to be 1/5 times this column 3, 4, 0, which is going to give us 3/4, 4/5, 0. U sub 2 is A, V sub 2 over 5, which is going to equal the column 0, 0, 1. So if we choose a third orthonormal vector, U sub 3, that equals this column, negative 4/5, 3/5, 0. So from there, U is going to equal the following matrix. First row, 3/5, 0, negative 4/5. Second row, 4/5, 0, 3/5. Third row, 0, 1, 0. Okay, so sigma here is first row 5, 0, second row 0, 5, third row 0, 0. V, first row 1, 0, second row 0, 1. So A is going to equal U sigma V transpose. And because the two singular values are equal, the best rank 1 approximation is not unique. So one valid best rank 1 approximation is going to be A sub 1 equals 5 U sub 1 V sub 1 transpose. And that's going to equal to 5 times the column 3/5, 4/5, 0 times this row 1, 0, which is going to come out to column 3, 4, 0, column 0, 0, 0. And also, if we wanted to, A sub 1 is a good choice. A sub 1, column 0, 0, 0, second column 0, 0, 5. That's a good choice too. And we can add the approximation error is going to be the following here. The 2 norm of A minus A sub 1, that equals 5. Okay, so going on to number 8. So number 8, we consider AX equals B, where A equals first row here for this matrix 6, negative 1, 1, second row negative 1, 5, negative 2, third row 1, negative 2, 4. Okay, part A, we want to construct the Jacobi iteration matrix. Part B, we want to construct the Gauss-Seidel iteration matrix. And for part C, determine the convergence using spectral radius arguments. So this is iterative linear solver problem. So we were given A, row 6, negative 1, 1, second row, negative 1, 5, negative 2, third row, 1, negative 2, 4. So we could say that A is equal to this sum D plus L plus U, where D is going to be equal to this matrix, first row 6, 0, 0, second row 0, 5, 0, third row 0, 0, 4. So the Jacobi iteration matrix is going to be B sub J equals negative D inverse L plus U. So B sub J is going to equal the following. The first row is going to be 0, 1, 6, negative 1, 6. This is after computation. Second row, 1/5, 0, 2/5, and negative 1/4, 1/2, 0 for the third row. And the Gauss-Seidel iteration matrix is B sub GS equals negative this quantity D plus L inverse U. So this is going to give us B sub GS equals the following matrix. First row 0, 1, 6, negative 1, 6. Second row 0, 1/3, 1/30th, 11/30ths. And third row 0, negative 1/40th, 9/40ths. So calculating from here, we perform the computation. The eigenvalues are going to be eigenvalues of B sub J are approximately negative 0.5769. 0.4479 and 0.12 90. So this row of this b sub j, that's approximately 0.5769, and that's less than 1. So the eigenvalues here of b sub gs are 0, 1/8, and 2/15. And so this row b sub gs equals 2/15. That also happens to be less than 1. So what we could say here is therefore both Jacobi and Gauss-Seidel converge, and Gauss-Seidel is happens to converge faster. Okay. And now moving along to number 9. So we have this double integral here, S being that sphere, and we're going to, sorry about that, double integral, that's vector f dot d s vector, where that vector f is the following: x plus x cubed plus y, y squared plus z, z cubed plus x. And s is the sphere. X squared plus y squared plus z squared equals 4 using the divergence theorem. Okay, so this is a divergence theorem problem. So this f equals x cubed plus y, y squared plus z, z cubed plus x. Finding the divergence with nabla dotted with that f. So, or del dotted with that f, 3x squared plus equals 3x squared plus 3y plus 2y plus 3z squared. And by the divergence theorem, we're going to get that this double integral along s, this f dot ds, that's going to equal the triple integral v here, integrated along that v, 3x squared plus 2y plus 3z squared dv. So the region is going to be the ball x squared plus y squared plus z squared less than or equal to 4. And by symmetry, this triple integral along v is y dv, that equals 0. And the triple integral here, v, x squared dv, that equals this triple integral v, z squared dv. And for a ball of radius r equals 2, this triple integral here along v, x squared dv, that's going to come out to 4 pi r to the 5th over 15, which is equal to 4 pi 32 over 15, which is going to equal 128 pi over 15 when we perform the computation. So this is more of the setup for this. So this double integral along s, f dot ds equals 3 times 128 pi over 15 plus 3 times 128 pi over 15. So this double integral here, f dot ds, equals 256 pi over 5. And I'm just going through this quickly, pronouncing some of the symbols, just briefly, not going into the whole formality of it. But that's number 9, and that's part 3. Thank you very much, and have a great day.